pull out any food or drinks during the show, and silence any electronic devices. With that being said, I can hand it over to our speakers.
All right. Can you hear me? Okay. So most of you know me. I'm Dr. Richardson, and one of my absolute favorite parts of our speaker series every year is seeing our students as they graduate giving talks about their capstone presentations and their capstone projects that they've worked on, oftentimes for more than just their senior year. Today is no exception, and we have two students in astronomy that are actually graduating a semester early, and both of them I've had the pleasure of working with for the last couple years. And so it's a pleasure today to introduce first Anthony Fabrega, or AJ. AJ's been working with me on understanding some Wolf-Rayet binaries, which he's going to talk about today. AJ is hoping that after graduation, he gets admitted to grad school, and he has some applications already pending, I believe. And so keep your fingers crossed for him. And without further ado, here's AJ to tell you about photometric models of wind eclipsing Wolf-Rayet binaries.
Hello, everybody. As Dr. Richardson and Eric so kindly introduced me, my name is Anthony James Fabrega, or AJ. Some of you have had me as TAs or as TA mentors in the past. So today I'll be presenting my research as Monte Carlo hammering out, so MC Hammer, if you caught that joke. I'm analyzing the photometric eclipses of wind eclipsing WR binaries. I want to give a special thank you to my mentor, Dr. Richardson, for putting up with all the stuff I've done over the years, which is a lot. And I also want to thank the URI Space Grant, as Embry-Riddle URI Space Grant, as well as the collaborative grant that funded this project. So to start out with, I'm going to do a brief introduction on what WR stars are. WR stars are a rare subclass of O star that are more evolved, more luminous, and hotter. The only difference really is that they have lost their outer H shell. These stars are really big dust generators for our galaxy, and what they end up producing are about 1 solar mass per 10,000 years. So like every 10,000 years, these stars are shedding 1 sun's worth of material out into the universe, which enriches the environment around them, and so we would like to know what that dust looks like. Particularly what's important about my system, about the systems I'm studying, is that there's some subcategories about whether their spectra has nitrogen, oxygen, or carbon in it. The main thing I'm focusing on is this weird subtype H for a few of the systems, which means that even though they've lost their H shell, they still have H in their spectra, which is a little bit unique, and we'll get into why that matters in a quick sec. So for some comparisons, this is a WR star, and this is compared to our sun. A WR star has lost its outer shell, so it's smaller on average than an O star. Some parameters for comparison, they're about 1,000,000 times more luminous than the sun, about 10 times more bigger size-wise, so radii, and then they're also about 20 times more massive. And an O star is just pretty similar. It's just the highest type on the diagram, on the spectral class diagram. So what am I studying? You have a WR star with this really strong stellar wind that's electron dense, and then you have this O star binary companion. This O star binary companion, if it gets eclipsed by this WR star's wind, there's this little region where we can probe the wind using the O star's light, and that can tell us something about the dust generation of these stars. So in particular, if I was to look a little bit at the orbit, as the O star goes around the WR star, you will see that a dip occurs only when it's eclipsed by the wind behind. So you get this 1 eclipse per orbital phase kind of shape. However, there's some very big parameters that go into this, such as the number of scatterers that are present, the inclination and mass loss rate of the system really encourage here. So if I just change a few of the parameters, you can get a curve that looks like this. A really different system, however, they're modeled by the same function. So what you get is this is what basically represents a high inclination, high mass loss rate system, where you get as the orbit progresses, it just drops in normalized flux. And that is the atmospheric eclipse we're studying. This is different than what you would expect in eclipses, where you expect one to happen before, like on this side, and on this side. We don't analyze that because those are called core eclipsing WR stars. I'm specifically focused on the wind eclipsed part. You will see later that a few of the systems I have hints of being core eclipsers in addition to being wind eclipsers, and I will point those out when I get there. So this is the theory of this these systems I've been studying, and I lost all the freshmen in the room, so I'm not going to go too much into it. If you would like to discuss the theory with me afterwards, you're very welcome to do that. I just wanted to demonstrate that the main parameters I'm trying to pull out from all of this math is mass loss rate, inclination, and the normalized flux continuum, because that tells us the most about the wind we're probing. So what is powering my research project? A Markov chain Monte Carlo pipeline that I have developed, currently going by the name Werewolf, the wind eclipsing repository for life curve fitting. And basically what it does is it's a random walk simulation where you start with some priors of what the guesses are for the system, like, oh, I think the system has this much inclination, this much mass loss rate. And then I just fit for those until it basically iterates through the process of, through the covariance of how well the data points are fit by the line, it'll iterate until it gets the best and highest probability fit. So, for example, this is an animation of what it looks like for one of the stars I've been studying. It started out pretty bad, and then as it iterates through the sampling, it will eventually find parameters that are best for the system. This is that star I told you about where it's pretty high mass loss rate, pretty high inclination, so it kind of goes off. So there's an exact physical representation in WR30 of that model I was showing earlier. So how did I start my project? I first started with this control case of comparing my model to what the work was done in La Montagne in 1996. They derived all the physics, and then I took it and wanted to use Monte Carlo to power it because it allows for more statistical analysis ways of developing the parameters. What I will say is I first started out with this very idealized model that assumes constant wind speed, and then eventually moved on to this beta equals 1 model. You kind of saw at that bottom is that massive equation. It accounts for accelerating winds, which of course is a little bit more difficult, to represent as compared to constant wind speed. But basically this control case was me comparing my model, the Monte Carlo model, to their generative evolutionary model, which as you can notice here and here, they match pretty identically with some small variation in the dip, but I can believe that's due to a variation in the model. It's within uncertainty there. What am I doing now? I started out with data that was not so great back in 1996 using the Paris Observatory, and it's 60 data points total for these really complex systems, which is not great. So under Dr. Richardson's guidance, I was able to get some archival test data where I have 1,000 times the photometric data using TESS, the Transiting Exoplanet Survey Satellite. So what does this do? Why does this matter? It allows for the larger statistical analysis. With 60 data points, every time you change something, it matters more statistically in what the numbers represent. When you have 60,000 data points, each individual point contributes less to what the fit looks like. But it allows you to do some really cool fitting with it. So the cons. When you transition your model from something that was really easy to do to a whole new another system, there's a few things you have to change. For example, I now had to add a phasing component where this was just given to me in phase, this was given to me in date, in truncated Julian date. So what you had to do was phase it to get into the orbit or into the period. And then also the main other thing is pixel contamination. The Transiting Exoplanetary Survey Satellite TESS is designed for exoplanets. So its pixels are rather large, and what that does is when you're observing not exoplanets with it, that can lead to some issues where there's background light contaminating your system, which I've had to correct for in some of these plots. I've been able to do this within 2 arc minutes approximately, and I've gotten some pretty constrained results doing this. Another question you might be thinking, if you know Monte Carlo or Python, runtime. Markov chain Monte Carlos are insidious for how long they take to run. Back when I first started and didn't know how to code that well, it took maybe an hour per run, and that is just sitting there at your computer waiting for it to spit out something. This is how I solved that issue when I eventually moved on to test data, where it really becomes an issue with 60,000 data points that you're fitting. So my solution was phase binning the data, which balances statistical accuracy with computation costs and exponentially decreases runtime. So how I did this was by taking each individual point or each individual sector of point. So I define a small range of phase, and then from that range, I just bin all the points to one point and average them there. So what I've done here is I've done it by square root n, or the number of data points on the plot. So for 60,000 data points, I've binned it into about 123 points. And what's really interesting about these two plots is it shows you that as you bin them, you can kind of see that there's some weird porosity / variation that shouldn't be happening, that we believe is kind of like if you have a wind that's perfectly exhibiting electrons like radially, you'll get a perfect line, perfect circle. But here, what you're seeing is that this might be more like leading us to believe that these winds might be more like a sponge, where there's holes every once in a while, because electrons are random walkers, where sometimes they're less dense and then other times they're more dense. So I want to present some of the results I've gotten for fitting various systems. Each of these is a little bit unique, so I'm going to go and talk about the personality of each star a little bit. So for WR12, this kind of represents a really high inclination, high mass loss rate system. Its inclination is about 80 degrees, and it has a mass loss rate of about 3 times 10 to the negative 5, which that means it's actually putting out 3 stars worth of material every 10,000 years. So this is like kind of the outlier of the system. So this is like the upper bound to test the model to see if it would work here. Then on WR21, I've also done it, but this is kind of the average system, if you will. Its average inclination about 56 degrees and about 1 mass loss rate. As I said, it was the average for a WR star. Now I have some really weird ones. So WR30 is a really high inclination system, but average mass loss rate. So it's that 83 degrees inclination, 1.21 times 10 to the negative 5 solar masses a year worth of mass loss rate. This is like one of those examples of how high inclination is really what affects the dip shape. Mass loss rate is a scalar to that, so it's as inclination's effects on the dip is way larger than the mass loss rates. WR31 is pretty unique. It's a middling inclination system, but it has noticeable wind rate, or like mass loss rate. So it's a little bit weird because that, like within errors, this could have wind or it could not, is what it's basically saying. So it's not as strong, but it still gets this really pretty light curve. These are the two brothers, as I like to call them. They're pretty unique, and these are the baseline models that I use to best correct the model that I've been using. So they're about average inclination, and they're also just on the boundaries of what you'd expect for WR star mass loss rate wise. These stars are pretty interesting because they have some weird variation going on, which is measured a little bit better in the standard deviation plots that I showed a little bit earlier. Here is a little bit of a unique system where you can start catching some burst activity potentially at 0.5, 1.5, and 0.5. And then these two are the really weird ones that are like really stress testing the model. WR148 is a really low inclination system, so barely noticeable inclination difference, and really high mass loss rate. And this proves my earlier point where with higher, inclination has the dominant presence in the dip size. So here what you end up getting is just this little curve. However, its high mass loss rate really does accentuate how important that both these parameters are in conjunction with each other. WR153 is a pretty unique system. It is not a WR plus O binary. It is a WR plus O plus O plus O, so it is actually a quadruple body system. And you can kind of tell that by how the fit looks compared to the data. The data itself has some more sinusoidal components to it. However, this system is pretty periodic, so we can fit the data pretty well here, even if it's not perfect. There is some slight eccentricity issues, as you can see by this curve being slightly slower, and then this one being slightly higher. How do we basically figure out what these parameters mean, and how do we figure out how the model progresses? First, the best way for the Monte Carlo is to do a corner plot. How corner plots work, if you don't know, is that they plot every point that for each parameter compared to other parameters, and then it creates regions of likelihood of which that point is going to fall into. So what you have here is a relationship, a very noticeable relationship between mass loss rate and inclination, which is really important to note because inclination is in an inverse relationship to mass loss rate, as I was showing earlier. As mass loss rate goes up, you'd have to expect inclination to go down, and the inverse is also true. There is some slight correlation between inclination and the continuum, as well as mass loss rate in the continuum, but those are pretty circular and are less dependent on each other. What does this help me do? It helps me find the parameter means and the statistical errors for each value. So you have these normal Gaussians, where you can find out what the mean values pulled out from the Monte Carlo system. And this is where you would find out, hey, this is what the means say about my parameters, about mass loss rate, inclination, and the like. So what's next for my project? The next step is to make my code open source. The pipeline will be made open source so that anyone who wants to do WR star research can take the project and import it and use it to supplement their research. There's always this issue in science about we have too much data that no one's able to analyze because there's no pipelines to do it. Well, this is kind of stepping in and being like, hey, here's a pipeline, use this to do it. So I have a paper in prep for some of the results you've seen. The acronym for werewolf, and if you wanted to understand where that came from. And then I will be presenting this research at the 247th meeting of the American Astronomical Society in January. And I will also be graduating, hopefully, and then going to grad school as well, hopefully. So I want to thank you for your time and for listening to my talk. Are there any questions? Dr. Bailey. Oh, no, okay.
Hi, thanks for the talk. It was great. I have a naive outsider question.
Okay.
You're talking about mass loss rate and inclination. In my mind, mass loss rate seems like a property of this system with this matter coming off of the star. Inclination, to me, seems like, oh, you just happen to observe it at this angle. Why are they connected?
Well, so if you go to, or if I go to this slide to a little, maybe it's right here. So, so the reason for why they're connected is that the mass loss rate is obviously intrinsic to the system of it's putting off this much material, but the inclination is the angle at which we're viewing the light, and dependent on the area, because it's a sphere around the star, if you look at it at different angles, there'll be different densities throughout the star that you're probing. So like if it's a really high inclination system, you might be only hitting the outside part of the wind, but you would be, but in the opposite way, if they're really tightly constrained, or not, if they're really tight systems, you would end up seeing a little bit more on the inclination side, so.
So it's like an effective mass loss rate. You're not getting what is the actual mass loss rate of the system?
Well, we're getting the mass loss rate as its base. So the mass loss rate is being probed by the O-star's light, and there's a relationship that basically takes that small section of mass loss rate that we're viewing, then we're basically rotating it around the star to get the entire mass loss rate.
Okay.
The model is basically assuming electron scattering in all this, and so you get a density of electrons that's causing the scattering, which you can then infer that if you have electrons in a certain type of wind, whether it's hydrogen rich or not, that gives you a mass loss rate. But the number of electrons in the scattering is entirely dependent on the angle at which you can view it. So AJ, go back one more to the picture, or to the diagram. So if the Wolf-Rayet star was more edge on, then you would have the light coming through more electrons, and you would see a bigger dip. Does that make? We can talk more later. Any other questions? Maybe time for one more. All right, Dr. Smith.
AJ, if you could go to the first WR star that you were looking at. And go back one, forward one. There. I was particularly interested in this. It looks like as you do the averaging to help optimize the MCMC, I don't know if it's my mind, but it looks like there's some periodic structure in there that's not fluctuations.
So if you're talking about this region right here, potentially?
Yeah, either one. But especially on the right-hand side, it looks periodic. There looks like there's some periodic structure when you take the averaging of the bins.
Yeah, so I am really grateful you brought that up because I forgot to talk about that. WR12 and WR30 are the two stars that have these core eclipse potential going on. So here you can see that the standard deviations of the data kind of just leaves the best fit line entirely.
Right.
That's because there's a small portion of the star that's being eclipsed by the photosphere of the other one.
Right.
So that there you get some periodic behavior there potentially, but then there's also should be some periodicity in some of the fluctuations you see here, because if the wind is rotating if you rotate about the wind, what you're going to see is that there's going to be holes in parts of the wind, and those holes don't close up instantaneously. So you're just going to be like, oh, in here, for example.
So is the angular velocity of the wind faster than the period of the star going around its host star?
Well, I know that the velocity of the wind can reach up to 2,000 kilometers a second, which I believe is typically faster than the speed of the angular speed of the star itself.
Yeah. What's the typical orbital period?
The typical, all of these stars are under 30 days, so they're pretty tight systems. The lowest end was 3 days of period, I believe. So imagine 20 times the size of the sun just rotating about each other every 3 days. Pretty powerful systems.
Okay, very good. Thanks.
Yeah.
Thank you, AJ. Let's thank our speaker again. All right, our second speaker today is Ms. Sola Nova. And Sola has been working with me for a little bit longer than AJ. And Sola actually has a paper that has been submitted to the Astrophysical Journal that we are working with a cranky referee on. But Sola has been an exceptional student and is, again, graduating a semester early this year. And she is going to present a very intense observational campaign we did on what's called the BE star, where Sola analyzed a lot of data, and she'll tell you all about that. So without further ado, Sola, are you ready? All right.
Yeah, I'm ready. Hello, everyone. My name is Sola Nova, and I'm here to tell you about the BE star Lambda Pavonis. During the summer of 2023, we were observing this star with the Space Telescope TESS, and right in the last few days of observation, we noticed an increase in brightness, which with these stars is associated with a disk formation event. So we ordered a spectroscopic campaign with 2 more instruments, Chiron and NRES, here on Earth, to try and learn more about what happened with this star during those couple months. To start, BE stars are spectral class B stars, so they're a little bit smaller than the stars that AJ was telling you about. And they have emission lines present, which is what the E stands for. These emission lines come from the disk itself. It's hot enough that it can emit its own light, and so we see that on top of the spectrum of these stars. Some other interesting things are that these stars are oblate in shape. They're sort of squished at the poles because they spin very quickly. Not so fast that they're going to break themselves apart, but a good estimate might be 2/3 of the critical rotation speed, being the speed they would fall apart at. And then, of course, the aforementioned disk, which is pretty interesting because it's not always present. It comes and goes at times. More specifically, Lambda Pavonis is a B2-3E star. So the B, it's massive. The 2 means that it's pretty hot. And the 3 means that it's kind of old. It's no longer a main sequence star, so it's somewhat evolved. So this disk, I've danced around it a little bit, but it's naturally the most interesting part of these stars. It's not always present. It comes from the material of the star itself, so it ejects this material into orbit. And that leads us to the number one question behind BE star research is, how does this disk form? What mechanism inside the star causes it to eject this material? And additionally, we might want to learn more about how this disk behaves while it's in orbit. So to do this, I will be studying the pulsations of the star, because that is one proposed mechanism that could give the star energy and launch the material into orbit. In order to do this, we need data. So the spectroscopic data from Chiron and NRES, it looks a little bit like this. This is for the line, the spectral line, helium-1 5876, and as you can see by this number, 07, July 7, 2023. This was before the outburst, so we're not really seeing anything interesting in this star. There's the continuum, there's a dip, and then it goes back to the continuum. So this is good, but naturally we're going to need a lot of data, like several hundred files worth of data. We collected 700 spectra, for which about 550 were from Chiron and 150 were from NRES. So now that we have this data, what's the other half of our data set? That is the photometry that comes from TESS. We only have 5 light curves, or 5 sectors of TESS data, so it's not equivalent to, say, half the data, but we've organized it into 3 specific light curves, with sector 13 coming from 2019, sectors 66 and 67 were from 2023, and you'll notice this uptick in brightness. That was the beginning of the outburst event. We don't think we captured the very peak of the event because TESS couldn't see the star after 1 or 2 days, which is kind of unfortunate, but at least we have a really good set of data to work with from TESS. What we'll do is we'll just make sure not to include this extra bit of data on the end, just in case it messes with our analysis later. As you may notice, these are sinusoidal in shape, and then there's little variations. So that's important to keep in mind when we get to the analysis later. For the spectra, what we want to do with this data is we want to organize it by date and by line. If we organize it by line, we can sort of see different parts of the star, particularly at different depths. And if we organize it by date, we can see when the disk formed or when it was gone, any interesting behaviors maybe qualitatively that happened. So you might notice in these red lines in each of the graphs, these are during the outburst, and there's this big bump in brightness, especially in H alpha, in H beta, and then there's the strong helium lines here. That is the disk in the spectra, releasing more light than the rest of the continuum. So now that we have this organized, what we can do is 2 forms of analysis. We have something known as equivalent widths here on the right, and what we do is we sort of measure the area of the line. That'll tell us how strong it is. Anything above this line subtracts from the equivalent width, and anything below adds to it. So you might notice that if we measured the area of this line during the outburst, we have a little bit of extra area in here, and this wasn't the best line to pick to show this, but that would subtract from the equivalent width. So we should find with time that the equivalent width will change as the disk forms. We know sort of qualitatively when it happened, but we can see more specific behavior with these quantitative analyses. Then on the right side, we have V over R, or violet to red. And what this does is we measure the area on one side of the line and on the other side of the line, and we take the ratio of the two. What you might notice here is, what if one side has more material on it than the other side? When we measure it, we would be able to see that as sort of an oscillating V to R ratio, especially if one side had more material at the beginning, and then it switched to the other side, and then back and forth. What that would equate to is the material orbiting around the star. So we would actually be able to probe exactly what happens with the disk from the start of the outburst to the end of the outburst. For the photometry, it's relatively simple. We just do a Fourier transform, and we get out of that oscillatory signals I was showing you before, we get specific frequencies. The reason this is important is because the two of these methods can come together in the meat of this paper, which is time series analysis. What we do is we stack up the spectra from the bottom to the top, all in a line, and then we phase by whatever signals we found in the Fourier analysis, and we get graphs that look like this. These were made from Levenhagen in 2011, and he was also studying Lambda Pavonis, and he looked at two helium lines. We specifically are going to be interested in helium-1 6678. We were able to look at this line as well in both Chiron and NRES. So first, we have to see if we find the signal that he found, which was 1.64 cycles per day. Then we take our spectra, we stack them up, we phase by that frequency, and we see if we get the same sort of signal that he did. What these graphs do is they basically visualize the pulsation. So from left to right, up and down, you are seeing the pulsations basically ripple across the star. So now for the results. Back to the disk behavior. I've shown here the original sector 66 and 67 from TESS, and I've marked in gray the periods of outbursts, which we defined as any point in time where there was emission in the spectrum. As you can see, the hydrogen has a much longer outburst time because emission was present for much longer than it was for the helium line. So the hydrogen took longer to decay than the helium. Of course, this is still quantitative, but we have some numerical results because we were able to fit these curves. The model for this sort of behavior is called the viscous decretion disk model, and they're described as exponential decays at the end, and what we did, even though it's not fully described in the literature, is we did an exponential growth at the beginning. And it seems, qualitatively, that they grow at the same rate. But as this table would show you from the disk growth parameters, within air, they grow at roughly the same rate, especially in the strongest lines. In the weaker lines, they didn't grow as quickly, but that could also be they're weak. They don't have as much to change in equivalent width. They change from 0.8 to 0.7. On the decay side, also quantitatively, we can see that the hydrogen lines did in fact take longer to disappear than the helium lines. And what this really says is, well, helium is heavier than hydrogen, and that means it would be closer to the star than the hydrogen. The hydrogen would be sort of like way out in the limb of the disk. So that would imply that the disk decays from the inside out, which is something that many other stars have observed to have. So what about the V over R measurements? First, the most interesting we found is that they do oscillate, which implies that the material was moving from one side to the other, and it decayed with time. I fit this with a sinusoid that was modulated with a decaying exponential. So over time, those oscillations shrunk. Down here, the most important parameters are that the period was basically the same in all of the lines, and this decay parameter here, or this time parameter here, tells us how long it took for those oscillations to decay, which was about 12 days within air. So what happens, what this seems to suggest, is that the material started on one side, and so the oscillations were huge because you have all this material moving back and forth between the two sides. But it slowly spread out over time, and the light on both sides of the star slowly became more equal until you had very small oscillations in the brightness. So the disk, or the star, emits a blob of material on one side of the star, and then it circularizes into a disk that then, after it has formed, it decays from the inside out. I did all of these fitting with Monte Carlo as well, and AJ explained a lot of how that works. So I just want to point out that we have one connected parameter, which is the initial time and the period. This makes sense though. If you look at this graph and let's say you nudge the time a little bit forward, then you need a smaller period in order to capture all of the data. And then if you push the time back a bit, you need bigger oscillations. You need bigger oscillations in order to capture all that data, which is exactly what this corner plot is saying here. Now, for the Fourier analysis, this is pretty simple. We found two signals, 0.163 cycles per day and 1.64 cycles per day. So we've confirmed what Levenhagen found. When we go into the time series analysis, we're going to look at 6678. I wanted to specifically look at the lower frequency signal first because it's a little bit rarer to see in BE stars, and you might be able to notice through the gaps that we do see those bars. And this is before the outburst, as denoted by these gray lines. So during the outburst, it's a little bit messy, but that makes sense because this data is contaminated by the emission. So after the outburst, we still have a very strong coherent signal. Okay, so that's good to know, but let's do a reality check with another line. We find in 4921, another helium line, it's coherent again before the outburst. During the outburst, it's still contaminated by emission, but I would argue that those bars are still visible even through the gaps and through the emission. And then after the outburst, it's still coherent. So Levenhagen did actually find this signal in his work too, but I don't think he phased it in these sorts of plots here. But what we can say, because of his results, is that this signal is very strong and coherent over many years. The more interesting signal is the 1.64 cycle per day signal. It's a little bit hard to see here just because that signal isn't as strong, so I added these blue lines to show where we should be seeing those pulsations. There's also this major gap, which is unfortunately taking away from the data, but we can't always be observing the star. And this was before the outburst in June and July. During the outburst, it's still contaminated with noise, so we're not going to see much there in helium 16678. And then after the outburst, that is definitely a different signal than what we had before the outburst. This might not be the cleanest, most coherent signal like the low frequency signal, but this is definitely different. And that's the most interesting thing that we're taking away from these pulsations in this work. We'll do the reality check again with 4921. Again, a vague signal that should probably be along this line. It'd be easier to see without this gap. Then during the outburst, we're not seeing much, but we'll chalk that up to emission. And then after the outburst, again, it's definitely a different sort of signal, despite the fact that we phased with the same frequency. So, as a bonus, before I run out of time, we have really fast pulsations as well. And on this scale here, it's hours, because we have singular nights of very dense data. So we stacked up the spectra again, but we didn't have to phase them this time. And this is just the way the spectra were captured in order. The most important thing to note is that line by line and night by night, these signals seem to be changing. Every night and in every line, the pulsations, and they're super quick. There's much more lines that seem to be traveling in different directions, and sometimes they switch speeds. That's the slope changing in those lines. So we have really quick photometric signals that are just changing every night. With that, for the future, we've already organized this work into a paper, and we're submitted for the first round of reviews. I've also presented this work about 6 weeks ago at the Flagstaff Symposium. And what we have to do next is we're still reworking those comments, but we plan to resubmit pretty soon. Hopefully we get accepted, maybe even before I graduate in a few weeks. And then in about 6 weeks from now, I will be presenting at the 247th AAS meeting in January in Phoenix. So with that, thank you for your time. Are there any questions?
Thank you, Sola. Are there questions today for Sola? All right, Dr. Bailey has one. No one else wants to raise their hand.
Hi, thank you for the talk. I have another naive outsider question. You're talking about outbursts, and I was wondering about the plots of radial velocity. If you had an outburst, I would expect that to be, if it's coming towards the viewer, be all blue shifted. Is that right? Can we see that on one of these plots?
The outburst.
Because here you have like blue shift and red shift because you have positive negative velocity.
Oh,
but does an outburst appear as just a blue shift?
So because the outburst creates a disk around the star, you will have parts in orbit that are red shifted because the material would visually be moving away from us, and you do have parts that are blue shifted as well as part of the orbit. So the outburst isn't like a ray burst that is traveling towards us. The outburst just describes that the star released material that formed into a disk.
It forms into a disk. Okay, thanks.
Hello, I'm not fully understanding how to read this phase versus velocity graph. What?
Okay, I can go into a little bit more detail. So we have phase starting from 0 going to 1. You always have to select some T naught, so we selected T naught to just be the beginning of the observations. The phase comes from, basically the way to think about them is they're bins. You take all of your date data, and when you modulate it by the frequency, you get these phase bins that all of the data end up in. So it doesn't look like this when you just stack them up by time. I do have a figure that shows what that looks like. I didn't include it in this presentation, but I could show you afterwards if you wanted to see that. So when you phase, what you're seeing is this velocity array down here is just telling you sort of the field of vision that you can see this star. So you're seeing to the left and right of the star. Oh, I switched sides. Did I go? I went that way. Okay, so when you start at phase 0, what this is showing is this is like a decrease in flux compared to the right side. So you have some high bit of a, oh God, I switched slides again. You have some high flux on the right side, which is like a pulsation. And because they're non-radial, I think that's the number one thing I forgot to explain. It's like one side is bulging and the other side is not. So with radial pulsations, usually you're expecting the whole star grows bigger and then shrinks. That's not happening in this star. It's like one side of the star is like sort of pulsing in one direction and the other side of the star isn't changing. This would be on, let's see, so the right of 0, this is like the right side of the star, and these lines here denote the edge of the star. One of these values was found in a previous paper. This 200 value we selected as seemingly the end of the star's like range, where the edge of its light would be. So these are on the star, and it's like an extra bit of not material from the disk. This is the star itself, bulging on one side, so it has more material, so it's brighter. And on the left side of the star, it's darker because that material had to come from somewhere. So what we see as phase increases is that dark spot where basically the bulge from the pulsation is moving across the star from left to right as time goes forward. Okay.
One last.
They're definitely complicated graphs, so I have no problem explaining that.
Did you have any theories for what caused the bulge on just one side or in general?
So the pulsations themselves, them being non-radial, in the literature, they describe two different types of modes, which are P modes and G modes. And it's been a while since I read it, but I think G stands for gravity modes, and P stands for pressure modes. So gravity modes would come from gravitational force pushing in on the star, and pressure modes would come from the radiative pressure. Basically, if you're getting non-radial pulsations, to me, what that implies is that you have it's a non-uniform pressure pushing out on the star in some direction. And gravity can combat that to some degree, which is why the star oscillates. But it doesn't, it doesn't stay like constant all in one direction. That's my understanding of the pulsations.
Well, I think these two students both did a fantastic job, and thank you both. And as a department and university, we wish you both the best of luck as you graduate and move forward with your careers. That's it for the Science Speaker Series this semester. We will be back. Next semester, we have a special Bring a Friend so that we get more people here. So make sure that you spread the word about how fun the Science Speaker Series is and how much fun it is to see your peers and other experts tell us all about different science that's going on. And have a great day and good luck with the end of the semester.